Oh, no, and you need this. Yes, I don't.
My email. Okay. Quickly answer Andre's question. So even with a linearized equation, you can look for power law solutions. And if you get an imaginary power law, that means there's an instability. And in fact, there is an instability. So, and the nonlinear stuff we haven't done, but for the SYK model, Klebanov et al. Have done it, and it's consistent with that interpretation. Okay, well, so thank you very much for organizing this wonderful conference, and I'm really enjoying it very much. And yeah, thanks a lot. So also thanks to Ilya for a very nice presentation, which leads in very naturally to things I'm going to talk about. So the summary is what I'm going to talk about, basically the same model as Ilya, but add in spatial disorder. And this is work done in collaboration with Ilya, How You Go, a student at Harvard, Avishkar Patel, who actually led most of the work that I'll emphasize towards the end. And he's online, so we may have to refer to him for some questions. And Maria Tikhanovskaya, who's a student who worked on certain aspects, which I'll mention very briefly. Okay, so let me just say a little bit about the SYK model, since many people have referred to it. I'm not talking about the SYK model, but it's a good playground to introduce the techniques that we are now exploiting to study more realistic models. I could take my mask off, I guess. All right, so the SYK model is a model with random interactions with no spatial structure. And the randomness, rather paradoxically, is very useful to solve it. And it doesn't, we don't believe it essentially changes the picture of a strongly interacting zero-dimensional model because the system is extremely strongly self-averaging. You can just take one sample with one set of numbers, and its behavior for all the correlation function we're looking at is essentially identical to any other set of parameters. And this is something you can now check numerically, and it works very well. So operationally, the way we solve the model is you take the average, since the system self-averages, and this gives you a sort of unusual type of theory where your fields are Green's functions and self-energies, which are functions of 2 times in this case. And so that you get some action, and this particular theory has been studied in great detail now, especially in the string theory literature. It's secretly a theory of quantum gravity of certain black holes, but I won't say anything about that. If you just take the saddle point of these theory, the large N limit, then you get these very simple equations. This is Dyson's equation, and the self-energy is basically the cube of the Green's function. And these equations we know a lot about. We can solve them exactly in the low frequency limit, and you get the square root of omega self-energy, and the coefficient here is known exactly in terms of the microscopic parameters. Okay, so that's really all I want to say about that model. But we're now going to apply the same method to more realistic models. And the model I'm going to consider is essentially exactly the model. First, let me review the model that Ilya just talked about. So you have a Fermi surface of a fermion psi coupled to some boson. In the case that Ilya talked about, it was the nematic order parameter, but this could be almost any boson. Could be a gauge field too. The most important point, as Ilya emphasized, is that it has 0 momentum. Most of the important fluctuations of phi are at 0 momentum. So we can take the simple coupling between the fermions and the boson, this Yukawa coupling G. And this, of course, this model has been studied a lot. And in particular, Sanksek Lee showed that the whatever the large N expansion, we just keep the fermions as flavor index, is not systematic. So this is one of the problems that we think can be cured by these SYK style methods, as was first pointed out by Ilya and York. So we introduce N flavors of both bosons and fermions and a fixed set of couplings that don't depend on space. Now the idea here, to address Eduardo's question just a few minutes ago, that if you just take any given set of couplings, just like the SYK model, it doesn't matter which ones you pick. At low energies, you'll get the same critical behavior. So if you think of it in an RG point of view, you have some huge space of couplings, and they all flow to the same fixed point. So that's the assumption, that ultimately there's some universal low energy behavior, which has a very wide domain of attraction. We can't prove that. In the SYK model, we can pretty much prove it by numerical study. This model, that's of course much harder. But with that assumption, then once you have this assumption that the low energy behavior doesn't really depend on which particular coupling you choose, you may as well average over the whole theory. And then you get this bilocal functional that Ilya mentioned in terms of 4 fields, the same notation that he used. And here's the explicit form of it. It's got both space and time. When you take the saddle point of this, you get the Migdal-Ilyashberg equations. And at low temperatures, there's an exact solution again, where all the coefficients can be determined, where the Green's function has some dispersion and a Fermi surface, which is sharp in momentum space, and a self-energy, which can depend on the direction in momentum space, but has an omega to the 2/3 self-energy. So this particular model, I would say, at least in the large N limit, is very well understood. And now the route is open, at least in principle, to computing those stringy diagrams that Ilya mentioned. Some of the sub-diagrams have been computed, but the full thing hasn't. That's really a daunting task. But there's no reason to expect that there's going to be any dramatic changes other than this small anomalous dimension of the fermion field that actually Max Matlitsky identified several years ago. So one of the things, just mentioning very briefly, we have computed in this larger limit is this out of time order correlation function. And what we find that at least in the large N theory, in this theory with full spatial structure, you have maximal chaos, exactly the value you get in the SYK model. All right, so now let's turn to something different. Let's compute transport. That's of course what we're all interested in. So this has also been computed, and many of the statements in the early literature of the transport property of this model were not correct. Basically, the answer is this theory, as written, has 0 resistance. That's because of the absence of Umklapp, or the Umklapp processes are exponentially weak generically on the lattice. So if I ignore Umklapp, then at 0 temperature, there's a delta function. Well, I think that's even true with Umklapp. There's a delta function at 0 frequency, and so the resistance is 0. What we do know, and this was something computed, there is no randomness. This is don't depend on space. It's translationally invariant. Yeah, so this is actually very important. I'm going to change that in a minute. But right now, let's just, this is the model that exactly the model that Ilya talked about. That has exact translation invariance. And as I emphasized earlier, we don't expect any low energy property to depend on what the values of the GIJ are. And you could just take any values you want, unless you take something really ridiculous, you will get this critical behavior. Yeah, that's, so the upshot is, to summarize what Ilya also mentioned, in the end, we're just solving the Migdal-Ilyashberg equations. But for the first time, I believe, following a proposal of Jorg and Ilya, there's a systematic way to justify that. That's what these random couplings buy you. Okay, so what one of the earlier results is correct, that at high frequencies you have this omega to the 2/3 behavior, and this will of course have various scaling properties. But as you get down to low frequencies, this thing has zero resistance. So the rest of my talk is, try to fix this, make this more realistic by adding some spatial randomness. So now we're going to really add something that's going to break translational symmetry. Okay, so now we're going to try to get more realistic. And I think, all right, so there'll be, I guess you'll hear various talks of other ways you could get rid of the delta function this afternoon. But I want to talk about randomness. Okay, so this is the model I've talked about so far, no spatial randomness. So let's just add the simplest thing, which is a random potential for the fermions. I mean, the entire theory of strongly interacting, of disordered Fermi liquids and interaction effects in disordered Fermi liquids is based upon this random potential. And now, if you give it the right flavor indices, this is very easy to incorporate in the whole formalism. I'll spare you the big bilocal functional, and then you get a larger limit with the saddle point and so on. So the techniques are very similar. I won't write down any of the steps along the way. So this is the most obvious thing you should add to this theory and ask what in the larger limit are the transport properties. So now, of course, the important point is this depends on R. And if you look at the correlation, the second moment of this, the delta function in space. That's what breaks translational symmetry, whereas here there's no space dependent at all for this coupling GIJL. Okay, so this is something we've been looking at for the past few months, and I'm just going to tell you about. I should really say it's been done by this part at Hayugyo, and I'll shortly show you some very recent and nice results by Avishkar. Okay, so what do you find in this limit? Well, first of all, the fermion self-energy has elastic scattering. This is just an impurity scattering term because there is impurities here. Okay, great. But then you see what that does to the boson self-energy. That previously was mod omega over Q. This becomes just mod omega. And so the boson propagated at the critical point has this Z = 2 form, Q squared plus mod omega. And when you put that self-consistently, which the whole theory is self-consistent, you get a correction to the fermion self-energy, which is this marginal Fermi liquid form. All right, so that looks pretty cool. And in fact, this will give you, you also have the free energy. Haven't computed it, but pretty confident give a T log T specific T. There's just one problem. Even though there is omega log omega in the self-energy, it does not appear in the transport. And that's roughly because this is essentially forward scattering. So there is so when you work out the transport properties, which is, again, the large N method tells you exactly which graphs you have to sum. It's basically a bunch of ladder diagrams with Slomazov-Larkin and Markey-Thompson type corrections. And when you work it all out, you find that this random potential only gives you the residual resistivity in the usual way. What you very naively imagine, if you didn't have any interactions, then there's some residual resistivity, which is dependent on the scattering rate, which is proportional to the square of the random potential. And if you look at the temperature dependent corrections, none of this marginal Fermi liquid survives, and you get just AT squared. Fermi liquid like, yes. Sorry? Diffusion? Yeah, so this is a resistivity, it's finite. It's just like a disordered Fermi liquid at low temperatures. 1 over n. Okay, well, there are the Altshuler-Aronoff type corrections. Well, they'll make it T to the 3/2 or no, sorry, yeah. But we're not looking at that. I mean, the point here is that we're in the quantum critical region where the inelastic scattering effects are so strong. Well, okay, down here in the Fermi liquid regime, you're right. We will have to worry about that. But okay, but it won't give you the quantum critical effects disappear, are basically removed by this random potential. Okay, yeah.
I presume here you also won't have maximal chaos, correct?
We haven't computed it, but I'm pretty sure you're right. Okay. All right, so maybe we should just give up. But then I guess this is something that goes back to also some of the works I cited earlier, some by Avishkar and others. Let's add now this G prime term. So we're going to make not just the potential random, but the interaction random. And this, you can view it as inspired from the SYK model, where also the interaction terms are random. So the idea here is that this G is the dominant term that creates the critical point. But then there's also this coupling constant that's random, which I call G prime. This is not meant to be derivative. Maybe I should make it a tilde. And this thing is a position function of space 2 with a moment, second moment that has a delta function. So it's a random function of position. And it's kind of natural. I mean, if there's a potential here, if there's some randomness here, this will very naturally feed into randomness over there. Okay. And now you can also take the larger limit with all three terms now and get some complicated set of equations that you have to solve. So we're still in the process of sorting it out, but I think Avishkar has figured a lot of things out. So let me just tell you what our current understanding is. So now if you look at the boson self-energy, remember there was this mod omega term we had earlier from the G. There's a similar term from the G prime. And again, this Z equals 2 behavior in the boson propagator. And if you look at the fermion self-energy, we have three terms coming from the random potential, the Yukawa coupling, and the random Yukawa coupling. The random potential is the usual elastic scattering. The Yukawa coupling gives you omega log omega as before, but this, as we already seen, doesn't give you anything interesting transport. And the random Yukawa coupling also gives you an omega log omega. But notice there's no V here. It has the same omega form, but the origin of it is quite different. I mean, same omega dependence and proportional to G prime squared. All right, so now you could take all these self-energies. So these two superficially look exactly the same. They both have the marginal form. But when you do transport, they are entirely different. And this is the punchline. Whereas this term does not compute with transport. This one does. The random interaction gives you, in fact, both marginal Fermi liquid self-energy and also a linear in T resistivity. This comes out very generically in 2 dimensions. Yes. No, so we can. I think this is what Avishkar may be better positioned to answer than me. He's just been working that out. This frequency dependence here would change, but we can work it out at V equals 0. This will change, but this will remain the same. Yes, yes. So basically, the bottom line is that there's 2 contributions to transport. There's a random potential that gives you the residual resistivity. And there's a random interaction, both in space. This is random in space, and this is random in space. And the random space term gives you a linear T resistivity. No, well, I have disorder, so no umlaut needed. So there's spatial disorder, absolutely. And it's quite generic, and in 2 dimensions, generic is linear in T. So, just knowing that it's an omega log omega is not sufficient. You really have to know the origin of where it came from, whether it came from, this kind of random potential, or it came from a random interaction. They have rather weak, significant effects, different effects. And you can now try to also look at mass renormalization effects and try to compute tau the way Andy McKinsey worked it out. There's something Avishkar has computed in a previous paper in the limit where this term is much larger than that term. And there you do get this universal Planckian behavior. When both G and G prime are present, well, it may be a little more complicated. We're still sorting all of that out. Yeah, but the thing we like very much is that residual resistivity has nothing whatsoever to do with the slope of the linear T. They're two different quantities controlled by very different things. Yeah. You would, you would. In fact, that's already in our previous paper and in an earlier paper. Yeah, you could put both of these to 0 and just have this. That's in our paper, which was published last year. But I didn't find that, that's a simpler case, of course, you can work everything out. And then, but that seems a little unreasonable for the physical system. This is, I think, much more reasonable where you have some uniform coupling and then there's a small disorder effects. Yes, yeah, so that's important. I mean, that's the main new result here. And the point is that, you know, this gives you a very singular self-energy, like omega to the 2/3 if the V wasn't there. This gives you omega to the 2/3, but the omega to 2/3 doesn't matter at all for the transport. The next term, which is omega log omega, is the one that controls the transport. And it gives you linear T resistivity. You know, this just comes out, but it's special to 2D. You don't have to tune anything, it's linear. Okay. All right, so I think that's all I have to say. I think, well, let me mention, Antoine said something about the random TJ model, which we cannot solve analytically, but we need all the sophisticated numerical methods that Antoine and his collaborators have developed at Flatiron. And after many years of work, we got this amazing phase diagram where you have this quantum critical region, which at least over a significant temperature range shows the, if you wish, a spin liquid behavior. It's like an SYK model of spin-ons. And in the same regime, you get linear T resistivity. And we have some understanding of this in the large M limit, although the residual resistivity and the coefficients don't come out right in that limit as coming from this time reparameterization mode, which is like the graviton of this G sigma theory. Okay, so to summarize, if you take a clean system with its translation invariance, you know, that's in the large N limit anyway, it's a theory of critical boson coupled to Fermi surface, and that has Planckian thermodynamics and maximal chaos, but it has zero resistance at zero temperature, or actually at any temperature. If you just take the long wavelength limit. But once you put in spatial disorder, then the linear T resistivity does arise from the first subleading order of random interactions. That's the key here, while the leading operator of random potential leads to residual resistivity. And also there's this T log T specific heat. The random TJ model we just mentioned, you know, has a superficial similarity, well, not super, I think very interesting similarities that it's that has got this Planckian behavior in relaxation times, and also a linear T resistivity coming from rather different mechanism, but also there it's clear that this is like the first subleading operator of random interaction. So it's quite interesting that you have to look at this random interaction correction in both cases. These are very different models, but again, it's this random interaction correction that gives you linear T resistivity in both cases. Thank you.
Hi, Subir.
Yeah.
This is probably a naive question, but you emphasize in the Ilya as well that you're looking at a Q equals 0 boson.
Yeah.
So is it a technical issue to the calculation if you have an antiferromagnet or finite Q, or you expect just the same thing will happen?
Well, we haven't, well, I mean, there's the same issues with the resistivity, but you could certainly apply this to the antiferromagnet and get, you know, justify the get the large N equations and get the Migdal. Yeah, you could do it. Yeah, I don't know what the transport looked like. It's just, this is a lot simpler, really. And also seemed to us, I mean, personal motivation, if you ask me what's going on in the cuprates, I would say, well, it's probably some kind of deconfinement transition. And there you have gauge fields and various auxiliary Higgs fields and so on. And those are pretty much all at zero momentum. So yeah, so there's various, I think it could happen there, but it'll be a lot more complicated. This is all just, what I've told you about is literally days old. So yes, give us some time. Or maybe you can work it out. Thank you.
Now I do. Okay, beautiful talk. I'm going to ask you a question that is a little off topic. Does this actually inform anything about the old problem of localization with interactions? Because in a sense, it seems to be like a piece of this theory if you go off criticality.
Yeah, well, no, I don't think so. That's a whole different types of low energy modes.
Well, okay, I looked at problems like that back in 1982.
I did too.
Yes, and the problem is that the 1/n expansion did not organize the infrared behavior completely in that. I didn't have random couplings. I have random potentials only.
I mean, Finkelstein and
It was done at the same time with Finkelstein.
well, but there was some subsequent papers by Finkelstein and what's his name at CUNY, claiming there was some large N expansion.
Yeah, it was never consistent.
You don't believe that? Okay. This particular large N trick, I think, is very powerful.
Yeah, so that's why I'm asking you.
Yeah, so I think the scope for applying it elsewhere is good. I mean, you may also be aware that in quantum gravity now, people are using this trick to see. There's a sense that if it's any semi-classical theory of gravity, can only come from an average of this type, and that's how you make sense of it. So it's a very universal trick, and I think there could well be many other problems of which it could be.
Okay, I will gravitate to that.
Yes.
Who's next? Okay, so I wanted to understand better the connection with Altshuler-Aronov. So if G prime is absent, your self-energy is the same as an Altshuler-Aronov in the Fermi liquid, omega log omega.
1 second. So let me just go. Let's see what are you saying. Let me. So what you're saying, G prime goes to 0.
Yeah, G prime is equal to 0, but you have V and you have G. So this omega up log omega is the same which you would get for Altshuler-Aronov.
This is coming from an order parameter, not from density fluctuation. So it's a little different.
Fine, but the
It has
form
the same form. Yes.
form is the same.
Yeah.
But then at the same time, there is a log T in the resistivity away from criticality. But if you take it, let's say, to 0 to 3.
I don't know. I haven't said anything away from criticality. But
right. But then I think Andy Millis and then Katrina and I and Internal Paul also followed what's going to happen with this log T at criticality. For Z equals 3, you get log squared T.
Yeah. So, I mean, I think those are all effects. They're not captured by this theory. All I'm doing in some sense is a certain large N limit and looking at the properties of that large N limit. And the large N limit focuses on the critical fluctuation of this order parameter or this boson or gauge field phi. There's a lot of other effects that happen in disordered Fermi liquids, which you're not including, that are not part of this theory.
Which can be larger than T, right? Which can be larger than T.
They can be larger than T, but at the critical point, I don't see how any of those give you what we are asking for here.
And just a follow-up. So if you only have G prime, only.
Yes.
Does it also contribute to the residual of resistivity?
No.
Why not?
Why not? Well, at least not in the large N limit. I mean, it will of course generate V at higher order than 1/n, but in the large N limit, it doesn't. It only gives you the frequency dependent self-energy.
Yeah.
Avishkar can correct me. Avishkar, if I made him wrong, he studied that very carefully.
Yeah, really clear, beautiful talk.
Thank you.
So we studied the nematic quantum critical point numerically.
Yeah.
And much to our surprise, found a T linear resistivity. We were expecting to find 0.
Yeah.
And presumably that's because of Umklapp scattering and because of this z=3, that even though we were coming as close as we could to criticality, we were far away. But
It calls also been issue with analytic continuation.
it could be an issue with analytic continuation. But so the question is, you know, can you put in Umklapp scattering here? Presumably that would,
Well, in principle, that's in Ilya's equations. He was solving the full lattice equation and has Umklapp in there. He hasn't done the full lattice equations for transport, but I think he's working on it. Where's it here?
I mean, so that should give you a finite, that should give you a finite answer.
Well, yeah, so I mean, Ilya's been working very hard at it. I'll let him speak. Yeah.
Very nice. Let me take this out. What happens as a function of disorder? Does anything happen to the linear in omega component in the scattering rate? Does it just, is it completely independent of V? Or does
It's
it
independent of
evolve
V, but it's
gradually?
not independent of G. I mean, again, you know, in a realistic system,
No, but in your equations, in your calculations, does it once you put it in, does it affect the linear in omega, the marginal part of the transport scattering rate, or is it now?
no, it doesn't.
So it's just a step function of V.
What, sorry?
Arbitrarily small V, G prime is there. The linear and omega part, the linear and T resistivity, I guess, is what I'm really asking.
Yeah, this
about.
is the, just replace omega by T. Okay, there's a term which is G prime squared times T.
In the
Okay,
limit,
the V equals 0 is a little bit complicated, but for the self energy is more complicated. But this will remain the same. Yeah, this is valid for any ratio of V and G prime. Sorry.
okay, thank you.
Well, so are you saying is there a quantum phase transition? I mean, sure, yes, there is a quantum phase transition. Right. So, well, I mean, oh, sorry, what's the? Well, okay. I mean, that's a whole different talk. If you want to go into the question of what this phi field is, there are many different possibilities. Of course, you know, the phi. This is the propagator of the boson phi, but there's a mass term here that Ilya studied in great detail. What happens to that mass term? I'm just put that mass term to 0 by assuming I'm at a critical point. And depending on, you know, if you take a gauge field, this is actually the mass term is always 0. Then you could even get a phase in general where things are critical. And if it's some autoparameter, depending on your autoparameter, you will get a critical point. I'm just looking at the critical point by setting this mass to 0. There's a lot of possibilities. You take this autoparameter phi, you can take any autoparameter which is at 0 momentum. Sorry, I keep going the wrong way. So this is the general ingredient. It's a very general framework where you have a Fermi surface of electrons and it's coupled to some boson. And depending on, well, so I'm doing it too. Well, I'm showing you how to solve it. Sorry? Well, I'm happy to make phi your favorite autoparameter. I have no problem with that, but I'm showing you how to solve it.
Yeah.
Randomness is crucial, absolutely. But that is exactly this result here. That is exactly thank you for emphasizing that. That's exactly the point here. It's a different coupling constant that determines the residual resistivity that determines the slope. That's something that comes out of this theory. You can,
Can I ask one quick last question?
sure.
Underlying of this is
Yeah.
that you keep saying that G prime is a correction, and so underlying is omega 2 third, which doesn't contribute to transport itself, but it's zero order theory. So we
Well-
have a practical question on this. You get this omega log omega at small frequencies.
Yeah.
What gives you the upper limit when you can apply this formula? Is omega 2 third in anywhere relevant for the upper limit of applicability of this formula?
It'll depend. Okay, so let me say what we're doing here. We are being very dumb. We take the large N limit, and we can now solve everything for arbitrary G prime, G, and V. There's a bunch of integral equations that we have to solve. They're complicated, and I'm just telling you the results.
Yeah.
That's huge. That's different from what we normally do with critical points. We do RG and this and that, and see which is relevant. You allow couplings to go. We've tried that for 20 years. So now I'm just going to solve the
but-
problem for all couplings.
But
Yes.
I'm asking omega log omega with G prime square coefficient.
Yeah.
Does it extend to all frequencies that you are studying, or there is an upper cutoff? For this?
They're depending on, they're certainly depending on parameters. We haven't worked all of this out. It will go over to omega 2/3 at higher
This
frequencies.
is what I'm asking. That
Yes.
There should be some scale above which it will go to.
Actually, not this term. This one will go over to omega 2/3.
But what about that one? The one that's relevant to you.
Well, okay, the short way to say it is really look at the boson. It's a little easier to look at the boson, which is, so this boson is a Z equals 2 boson.
Right.
So there's a crossover at some scale to a Z equals 3 boson.
Mhm.
And that scale is determined in some complicated way by the values of G, G prime, and B.
Absolutely.
I don't know the answer to that. Again, maybe Avishkar can put an answer in the chat. But yeah, I mean, these are things, if the, very nice, the work that Ilya showed you had a lattice and had a G. And I don't want to put a lot of work on Ilya, but he can put a G prime and a V in his equations and give you the answer to that.
Real question is how many parameters we can set to 0 and still get your result?
The simplest theory where you can get this, you will get, in fact, resistivity going to 0 at 0 temperature, is a theory where you put V equals 0 and G equals 0. And that has it's just a marginal Fermi liquid down to 0 temperature.